we're going to pick up today where we left off last time, which is with acetal formation and hydrolysis. I just want a brief review of acetal formation because I want you to see what we're talking about today as different manifestations of the same theme. And the theme is we're going to use an acid catalyst. Oh, I get to take this off now. Haha. We're going to use an acid catalyst to change who's the good leaving group on the tetrahedral intermediate. So recall in acetal formation, the neutral alcohol is not a good enough nucleophile to attack the carbonyl carbon directly. So we first must protonate the carbonyl oxygen. That generates an oxonium ion that's more reactive. And now the neutral alcohol can attack. When you do that, you get a tetrahedral intermediate. And at this stage, we start asking who's the good leaving group. Right now, it's the methanol group that just barely attacked. And it would be perfectly reasonable for this oxygen to, on the OH group, neutral oxygen, to kick down and kick off that leaving group. Doing so would take us back to the previous step. But if you look where we're trying to get, we need to get rid of that OH group and replace it with another methanol group. So what we do is we use our acid catalyst to remove the proton from our methanol oxygen. That turns it into a neutral ether type oxygen. And now we have an intermediate where there isn't a good leaving group. This intermediate has a name. Your text identifies it for you, and I'll point it out now. It's called a hemiacetal. Hemi because it's halfway to the acetal. We've replaced one of the carbon-oxygen bonds with a bond between carbon and the methoxy group. Hemiacetals are generally not stable because in acid catalysts, they're higher energy than either the aldehyde starting material or the acetal product. And so in the presence of acid, they will go either to here or here. They can also fall apart in base. We won't talk about that or worry about that. Hemiacetals are generally not stable. There is an exception to that. If the hemiacetal can be cyclic, it can be somewhat stable. That's important for carbohydrate chemistry, and we'll talk about that a little bit later today. We then use the acid to protonate the OH group, thereby converting it into a good leaving group. Now the neutral ether or methoxy oxygen is strong enough to kick down and remove water as a leaving group. We talked last time about how you can drive this equilibrium forward by removing water, which promotes product formation. When water leaves, we're left behind with another oxonium ion. The difference between this and the other oxonium ion we encountered earlier is that this oxygen was positively charged because it was protonated. This oxygen's positively charged because it's, in addition to the pi bond and the sigma bond here, it's bonded to an alkyl group. At that stage, neutral methanol can attack to generate this tetrahedral intermediate. Again, that methanol that just attacked is a good leaving group, but we can change it to not a good leaving group by removing a proton, and that gets us to the acetal product. Okay, so using proton transfer to swap who's the good leaving group, all of these are equilibrium steps. We drive the reaction forward by removing water. Okay, any questions you want to ask about that? Okay, so questions you want to ask about that acetal formation mechanism? Yeah?
How strong does the acid have to be for the acetal?
How strong does the acid have to be for the acetal to form, for the catalysis to work? This is a pretty strong acid. Acetic acid is a little bit weaker, but that would work too. Yeah, just enough. I guess that's not a great answer, but yeah. What else? Yeah?
The reverse reaction, do you need an acid at all, or just hydronium?
For the reverse reaction, do you need an acid at all? Hydronium is an acid, but in water. So the key for going forward is you're using a solvent that's not water and you're removing water to drive the equilibrium forward. You want to go backwards, just use an acid in water. Yeah?
You need to remove water
Yeah, and you can remove water just by distillation or some other procedure. You can put in a hygroscopic salt that will soak up the water, anything that will take it out of the equilibrium. And you don't have to write that, that's a big paragraph that you could put here, and you don't need to write that. If you're using an alcohol with a catalytic amount of acid, we're going to assume that you're removing water so that you can form the acetal. All right, so I don't want to spend forever on the acetal hydrolysis mechanism. We started that last time where we had this interesting cyclic acetal. It may look weird to you, but it has two oxygens bound to the same carbon. So that's, and these oxygens are each bonded to a carbon. That's a typical acetal. Even though those two carbons are attached to each other, you can basically ignore that here and just imagine it as though it were this. And if you want to do the mechanism for acetal hydrolysis, all of the intermediates are the same on the way back. You just have to push arrows in a different direction. So notice that with our acetal, the penultimate intermediate is the one where one of our two acetal oxygens is protonated. So I can draw that intermediate here as we did last time. And then how do I get from here to here? Well, what changed? I have a new oxygen-hydrogen bond. How did that form? It would have had to involve our acid catalyst. So those are the arrows I use for proton transfer. Similarly, if I look at the intermediate that precedes this one, now it looks like one of my alcohols is no longer attached to the carbonyl carbon, and I should have a positively charged oxonium ion. In this case, that would look like this, where one of my acetal oxygens has left as the neutral ORH group, and then I have this oxonium ion, and so on. So we can continue the mechanism from here, and we'll do this just briefly as a review. Notice that what I want to do as the reaction progresses is I want to ultimately liberate the alcohol and get back to this aldehyde starting material. So how am I going to do that? Well, I'm going to need to have this oxygen ultimately leave. I need to replace it with an oxygen from water. So water attacks and I get this intermediate. Again, I have water as the good leaving group, which this neutral oxygen lone pair electrons could kick down and kick off that leaving group. That would just take us back here. But if instead we use our conjugate base of our acid to change who the good leaving group is via proton transfer swaps, we'll get to this intermediate, which is the hemiacetal. And in this intermediate, as we've mentioned before, there are no good leaving groups. And now we're going to protonate the other oxygen so that we can convert it into a good leaving group. That looks like this. Let's see. At this stage, I think some of you are likely wondering, how do I know which oxygen gets protonated? And the answer is all of this is going on in aqueous solution, but only these steps lead to the products that form. So we're not going to worry about, some of you may be thinking, well, what about this oxygen? Does it ever get protonated in acid? Sure, it does, but then the proton comes back off, and if that equilibrium doesn't lead to products, it doesn't really matter for our purposes. Now that we've converted the alcohol group into a good leaving group, now the neutral oxygen is strong enough to kick off that leaving group. So that gets us to this alcohol product, and Well, it's starting to look like an aldehyde, only the carbonyl oxygen is protonated. So to get from there to our aldehyde product is a simple matter of using the conjugate base of our acid to remove the proton, and then we get the aldehyde. And again, the thing that's going to drive this to completion is the fact that you are adding an excess of water. And under acid catalyzed conditions that facilitate this equilibrium, the excess of water is going to push you towards the aldehyde product. All right. Questions about that? Yeah.
So the base in this reaction is water, like HA.
Right, HA in this case would be, and I'm just abbreviating it out of laziness, but that would be hydronium, and then A minus would be water. Yeah?
Do we have an H come off in some of the steps, the bottom one?
Do we have a hydrogen come off in which of these steps? Oh, yeah, you're noticing that I, again, forgot to put in the aldehyde hydrogen. Yeah, that stays there the whole time. It's not involved. Sorry. Okay. Anything else? Yeah. Are the last two steps equilibrium as well? Yeah, they are. Sometimes I forget to draw that. And frankly, there's no points assigned to whether or not you remember to draw equilibrium arrows. So it's just for your edification. You guys love stuff that's just for your edification, right? Okay, what else? So let me show you some examples of acetal chemistry that comes from biology. And we're going to start with just a brief introduction to carbohydrates. Let me just reassure you that you don't need to memorize these structures yet, I guess. So we're going to draw here the structure of glucose. I'm going to draw it in kind of a strange way for a linear molecule, but you'll see why in just a little bit. So glucose is a 1, 2, 3, 4, 5, 6 carbon sugar. It's a carbohydrate because it's called that because for every carbon you have basically a water molecule. For every C you have H2O. And glucose is, of course, the input to glycolysis, and so it's very important in metabolism. Interestingly, glucose is an aldehyde, and aldehydes are reactive. And we'll talk maybe today, maybe next time, about the consequences of having high glucose levels in your blood. That aldehyde can react with stuff that you don't want it to react with. And that reactivity is the origin of the problems that happen with elevated blood sugar in diabetes. But it turns out that glucose doesn't, in aqueous solution, the open chain form of glucose is not the predominant form. It turns out that even with the small amount of acid that's present in pH 7 water, you can form, and we won't draw the mechanism of this, but it's just exactly the same as the first few steps of acetal formation. You can protonate this aldehyde oxygen, and then this neutral oxygen on carbon 5 can attack the aldehyde. And when it does, after the appropriate proton transfer steps, you get this closed chain structure that looks like this. So this is the cyclic form of glucose. We will call this a cyclic hemiacetal. And you can see here's the aldehyde proton. Here is our let's see, no, I don't like that color. Here is our sp3 hybridized carbon, where one of the groups is an OH and the other is the oxygen from the ring, but you could think of this as just another OR group. So you should see the similarities between these two structures. You may have seen drawings of glucose before that looked like this. That's a particular way of representing the glucose ring and the stereochemistry, but it adopts a chair conformation. So this is the glucose molecule, and it's a hemiacetal. We'll talk more about carbohydrates later on. There's two possible stereochemical configurations at this carbon. That's the hemiacetal, and we'll talk about what happens if it's up versus down. So that's a hemiacetal. Let's just briefly show you some applications of acetals in biology. There we go. So it turns out that, as you could imagine, sugars have lots of OH groups, right? And so you can link one sugar to another by having one of these alcohols on another sugar molecule be the second alcohol in acetal formation. So what if we linked two glucose molecules together? So here is the first one. And it's an enzyme that does this. So what would happen is that the enzyme would catalyze turning this OH into a good leaving group. It's not a good leaving group now, but it could be if we protonate it. And I'm drawing this for you not because it's important to memorize the structure, but I want you to see how what we're doing applies to biology. So if you compare what we're doing now to what we did above in acetal formation, we need to get rid of water as a leaving group to make a place for the new nucleophile to come in. So electrons on that neutral oxygen kick down and water leaves. We get from that an oxonium ion. You're going to think it looks weird and strange, and how would I ever draw that? But go up and compare it in your notes later on to the corresponding step in our simple acetal mechanism, and you'll see that it's exactly the same. Here's, if you replace this with an R group and this with another R group, it will look exactly like the oxonium ion above. Then we could bring in a second molecule of glucose, and the enzyme would of course direct which of these OH groups was the nucleophile. That's the beauty of enzymes. They can take, by holding on to a molecule in a certain way and bringing it to another molecule with a certain orientation, they can control which of those OH groups does the chemistry. In the lab, that's really hard to do. And my colleague Paul Savage in his lab, they've gotten very good at using elaborate protecting group schemes to prevent all of the alcohols from reacting except the one they're interested in. And it's really hard, and it takes people their entire PhD to do it. So the fact that enzymes are so good at it is really beautiful. In this case, for the example we're going to use this OH group on carbon 4. That will attack the oxonium ion. And what we're going to get from that is the following disaccharide, which is a pain to draw, like I said, but I want you to see how this applies to biology. let's put the proton here. And then the enzyme or the conjugate base of our acid, whatever it is, can remove the proton. And that will give us our final acetal. Oh, the horror, right? You hope you're good at drawing chairs, right? Because this is painful. Okay, so that's a disaccharide. Can you see that it's an acetal? Can you see how this is our carbonyl carbon and these are the two OR groups and this is the aldehyde proton? Okay, so some of you may have some questions about this step. How do we know that this OH group attacks the oxonium ion from below so that the stereochemistry of this oxygen is down? And the answer is you wouldn't. You couldn't. It would be difficult to control that in the lab, but the enzyme does that depending on what the identity of the enzyme is and what the needs of the body are. The acetal with this particular configuration, this is called an alpha linkage, where the oxygen from the other sugar is axial and down. That's called an alpha linkage. I don't know if you've had some cell biology, I don't know if you've learned this terminology. You will certainly use it if you take biochemistry. If we number the atoms of the sugar, 1, 2, 3, 4, 5, and 6, we can describe this linkage between the two sugars as alpha 1, 4, because the oxygen on this acetal carbon, the oxygen for the other sugar is down, and because we're linking carbon 1 and carbon 4. So if you've heard of an alpha 1,4 linkage, that's where this is coming from. It turns out this is the kind of linkage that's present in starch. So if we were to, and in starch, you've got a whole ton of sugars linked to each other. So you don't have to draw this, well, if you want to, you can draw this, but this is sort of the structure of starch, is a bunch of sugars linked to each other via this alpha 1,4 linkage. And sugars with this kind of shape or this kind of linkage tend to adopt spiral sort of structures, and so that linkage between each individual carbohydrate gives the carbohydrate a particular shape. I forgot an oxygen there. So that's the structure of starch, or amylose. Okay, in contrast, if you take the same sugar and link it together with the oxygen on the other sugar up, you would end up with this kind of extended shape. And if we fill in the OH groups here, and don't worry about copying this down, you can get it from the notes later, and in any case, I'm not going to ask you to memorize it. But I just want you to see the structure. This is cellulose, okay, which is fiber. Notice the only difference, first of all, notice the acetals linking individual sugars together. Do you see that functional group there? It's going to take you a little bit of practice looking at that and seeing that functional group, but those are acetals. But notice that the stereochemistry, where the oxygen of one sugar is down relative to the ring of the other sugar, that defines starch. But if we have the oxygen up relative to the ring of the other sugar, we've now got cellulose. Now, as you know, we can hydrolyze, our body can hydrolyze the linkage in starch. We can do reverse acetal formation or acetal hydrolysis to liberate glucose molecules. We can do that from starch, and that's how we get a lot of carbohydrates. We don't have in our body the enzymes to hydrolyze that particular linkage, which is why when you eat a lot of cellulose and fiber, it goes in your mouth and out wherever. Anyway, we'll leave that for biology class. But it's this stereochemical difference, which is why you and I can't eat like a bunch of lettuce. This is why lettuce doesn't have hardly any calories in it. It's not that it doesn't have sugars in it, it does, but they're a linkage that we can't get glucose out of. All right, anything you want to ask about that? We'll return to carbohydrates, but yeah.
So why can't cellulose like interconvert its chair conformation to make starch?
Why can't cellulose interconvert its chair conformation to make starch? There are organisms that can do that. We just don't happen to have the enzymes. Cows that eat grass, ruminants, they have microbiome in their guts that helps break this apart, but it takes a while. Yeah. One other thing that might be interesting to you is the structure of lactose. You don't have to memorize this, but it's something that affects a fair number of people and actually has a huge amount to do with the history of humanity and evolution and travel. So I don't particularly like those chairs, but I'm kind of in a hurry because I want to show you this. So this is the carbohydrate lactose. It has two sugars. You'll notice this one over here looks almost the same as this one here, only the OH group on carbon 4 is up instead of down. So this sugar is galactose, and this sugar is glucose. The linkage between sugars is a beta-1,4 linkage. And lactose is a carbohydrate that's found frequently in milk, okay? And there's an enzyme that can hydrolyze this linkage to break the acetal into its component sugars. It's called Beta-Galactosidase. Ases are enzymes that hydrolyze stuff. Beta is because of the stereochemical configuration. Galacto indicates that you've got galactose here. So interestingly, human infants that depend on milk for survival and nutrition their intestines express a lot of beta-galactosidase, okay? But for many humans, historically, expression of beta-galactosidase decreases as the human grows older. Why? Because the human no longer survives on milk, at least not our ancestors before the dairy industry was a thing, right? Before ice cream. So what happens if your intestines no longer express a lot of beta-galactosidase is you don't have the enzyme to break this apart, and so you have to rely on bacteria in your microbiome to do that, which is okay, except that can result in bloating and intestinal cramping and all of the things that are associated with lactose intolerance, right? Folks that are lactose intolerant don't make enough of this beta-galactosidase. Turns out that was most humans, and I forget how many thousand years ago, but the genetic evidence suggests that at some point in Europe, as humans, and of course humans migrated out of Africa into the rest of the world and into Europe, but at some point in Europe, a mutation occurred that allowed beta-galactosidase to persist in the intestines, and this presumably created an advantage because people that had that could gain nutrition from milk and cheese is a great way of storing nutrition for a really, really long period of time, right? The stinkier the better for cheese, right? So it turns out that if your ancestry is from Europe, you are less likely to be lactose intolerant because of that mutation thousands and thousands of years ago that made enough beta-galactosidase in your intestines to handle this stereochemistry. If you're from somewhere else, if your ancestry is not from Europe, then you may be lactose intolerant. And that's just an interesting remnant of human history that we deal with all the time. If you take a lactose aid, it likely is just this beta-galactosidase. Thankfully now, even if you're lactose intolerant, you can enjoy the deliciousness of ice cream. All right. Anything else we want to talk about? Yeah.
So for the people that do produce the beta-galactosidase, they can break down the lactose into galactose.
That's right. They can break down the, yeah.
And then does everyone have enzymes that break down metabolize the galactose?
Does everybody have enzymes that can metabolize galactose? I think so. Galactose is involved in a lot of different places in humans. So yeah, you can use it. I don't know the biochemistry well enough to say whether there's an enzyme that converts galactose into glucose, but we can look it up. In any case, once you break it apart, it's not a problem anymore. So yeah, people that have enough beta-galactosidase, they can break this apart, metabolize the glucose, use the galactose, and so on. All right, cool. So that's probably enough on acetal formation, except for, I guess I do want to show you how you can use acetals as protecting groups. So this will be more of an organic chemistry application instead of biochemistry. Let's imagine that we have an aldehyde here and an alcohol here. I don't know that I like that. Let's imagine that, let's imagine that we have an ester here and an aldehyde here. And let's imagine that my desired product is to have the aldehyde survive, but I want to convert the ester into the tertiary alcohol. So if I were doing this, looking at this synthesis, and I saw, okay, I need to convert an ester into a tertiary alcohol, I would say, two of the same thing attached to that tertiary alcohol. It looks like I'm going to use an organolithium reagent or a Grignard reagent to attack the ester, right? Attack, get the tetrahedral intermediate, and so on. The problem is that if I did that, if I actually tried to use the corresponding organolithium reagent, instead I'm going to get the undesired product, which has the result of the organolithium reagent attacking both the aldehyde and the ester. Okay, so this is what I want, but this is what I observe. So I need to do something to the aldehyde to turn it into something that's not going to be a good electrophile. So one of the things I can do instead, if this approach doesn't work, one of the things I can do instead is, first, I use some alcohol. Let's just use this alcohol where the two OH groups are on the same, in the same molecule. And then let's use catalytic acid. In this case, I'm going to use para-toluene sulfonic acid like we did before. and we're going to be removing water. It turns out under these conditions, you can make the acetal without messing with the ester. The ester is stable to acetal forming conditions. So you could make this acetal where the two OH groups are, the two OH groups from the alcohol are both attached to each other. You make that acetal first. Okay. Now the acetal is not a good electrophile. It doesn't have a low-lying empty orbital. There is no pi star. The carbon-oxygen sigma stars are pretty high in energy because carbon-oxygen bonds are stable. So now I can take my organolithium reagent and do the reaction with the ester. So in a second step, I'll work up with water to give me my ester. And then finally, I can remove the acetal under strongly acidic conditions in water, and that gets me to my desired product. So acetals are our sort of second protecting group, and people use them all the time in organic chemistry. It turns out if you have a molecule that has OH groups on it, you can actually use an aldehyde as the protecting group for those OH groups, but I won't show you an example of that. Okay. Questions? Yes?
Then you just treat it with acid to get rid of that.
That's right. Then you just treat this with acid to liberate the alcohol, which is a byproduct I haven't drawn, and then the aldehyde is back. Yes? Does it have to be hydronium? It needs to be aqueous, and any acid in water is probably hydronium. Okay, what else? Yes?
So you use PTSOH and hydronium separately. Can you use like the same acid for both like protection and deprotection?
Could you use the same acid for protection and deprotection? Yes, except I'm not sure toluene sulfonic acid is soluble in water. I don't actually know. I suppose you could use acetic acid here and again here. The key is you're removing water versus adding water. Yes?
I'm a little confused how you formed the nanofusion.
How did we form the little guy here? Yeah, so first we protonated the oxygen. Then one of these oxygens from the alcohol attacked, and we made the hemiacetal. I showed up here the reverse process. So ignore the arrows for the moment. Let's start with the aldehyde. We protonate the oxygen to get this intermediate. Then one of these OH groups would attack to give you this intermediate. You'd remove this proton to get the hemiacetal. Then you would trade who's the good leaving group by protonating this oxygen, turning it into water, and these electrons would kick down and kick off water to give you this oxonium ion, whereupon this other OH group would attack the carbonyl carbon, now in an intramolecular fashion. That's a 1, 2, 3, 4, 5 membered ring, to give you this intermediate, and then you'd get to the acetal by simply removing that proton. So that's the process. Yep. Okay, what else? Yeah?
You use the TBDMS and TBAF, or the other protective groups that you use as well?
Okay, good question. Could we use the silyl ether protecting group, that TBDMS group that we install? In this case, no, because I don't have an alcohol functional group. If I were going to try to protect an alcohol, that would be great. But instead, I'm trying to protect an aldehyde, and TBDMS chloride doesn't mess with that aldehyde oxygen. Yeah. Okay. Yeah.
Is that the TBDMS? That's pretty much exclusively for alcohol?
The TBDMS group, for our purposes, yeah, will be exclusively for alcohols. Okay. Okay. Well, while we're on the subject of glucose, let me show you a reaction that can happen when you have too much glucose in your blood. So for our purposes here, we're going to remember that glucose, even though it exists predominantly in a cyclic form, cyclic hemiacetal form, can form an open chain, has an open chain form in equilibrium with the cyclic form, and that open chain form has an aldehyde on carbon 1. And remembered, like we talked about earlier, the cyclic glucose is a hemiacetal. That functional group is right here. And opening that up is just exactly the same mechanism as we did previously for opening up this hemiacetal. Okay, so glucose is an aldehyde, and aldehydes are reactive. I'm going to abbreviate glucose now. You'd be like, thank goodness, with this big R, okay? Now, what types of nucleophiles do we have in biological systems? One of the most important nucleophiles we have is on proteins, and it's an amino group, a primary amino group. So there is one of the 20 canonical amino acids is called lysine, and lysine has an amino group on it. And most of the time that amino group exists in a positively charged form, but there is at pH 7 a small amount of the neutral form. And let's just put a squiggly line here to indicate that there's something large on this end. This is going to be a protein, okay? Actually, let's suppose it's hemoglobin. But we're going to abbreviate that as R and H2. Is that okay? All right. So what can happen? The neutral amine probably doesn't attack the aldehyde first. Probably we need an acid catalyst, but at pH 7 there's enough hydronium present to protonate the carbonyl oxygen. I'm going to assume you know how to do that with an acid, okay? I'm not going to draw that here. It doesn't magically happen. You'll have to fill in the blanks in your brain. But then that amino group can attack the electrophilic carbon, attack the pi star of the carbonyl compound, breaking the pi bond, and we get the familiar tetrahedral intermediate. I want you to focus on what's similar here to things you have seen before. This intermediate should look to you a lot like, sorry for the disorienting scrolling, this intermediate should look a lot like the following intermediate from acetal formation. Here's the sp3 hybridized carbon. Here's an OH group. The only difference is instead of an alcohol group here, we have an amino group. You see the analogy? We're just using a different nucleophile, but the same chemical steps. All right. I think I'm going to get rid of that to avoid confusion. Right now, as we saw before, this amino group is positively charged and could leave as a neutral amine. That would just be going back to the previous step. But if instead we use the conjugate base of our acid to remove one of the protons, that will get us to an intermediate that looks like this, where the amino group is no longer a good leaving group. This structure should look like a hemiacetal, only one of the groups, instead of being an alcohol group, is this amino group. You could call this a well, actually what your book calls this is carbenolamine, which is terrible. You could also call it a hemiaminal, I suppose. But what we're going to do now is change who the good leaving group is by protonating the oxygen with our catalytic acid. When we do that, we convert the neutral OH, which used to be a poor leaving group, into OH2, which is a good enough leaving group for nitrogen to kick off the OH2 group as a leaving group. Water leaves, and then you get this structure. This looks like an oxonium ion. It should compare directly to, it should compare directly to this intermediate in acetal formation / acetal hydrolysis. I'll erase the arrows, but you have a new carbon-nitrogen double bond here instead of a carbon-oxygen double bond, but you have a positive formal charge on nitrogen and an R group there. Now in acetal formation, what we typically do is have another OH group attack here. The difference between acetal formation and what we're doing now is that we have an acidic nitrogen on our ion intermediate. And removing that proton to restore the acid is a lot quicker than another nucleophile attacking at the carbonyl carbon. So we remove the proton there, and then we get this neutral compound that is stable. And this is called an imine. Okay, not an amine, A-M-I-N-E, but an imine, I-M-I-N-E. And the ion that came before it that was positively charged is called an iminium ion. So the products are different from acetal formation. The mechanism is exactly analogous. So I don't want you to think of these as two completely different reactions, but rather two manifestations of the same basic reactivity. Now, what's the story with diabetes? Well, if you've got hemoglobin here, and you have a nitrogen on hemoglobin that gets tied up with the aldehyde from glucose, if it's okay, I'm gonna draw it this way. Here's hemoglobin, here's a nitrogen from a lysine side chain, and then here's the imine, where R here equals the rest of glucose. What you've got really is glycated hemoglobin, where this is the glycan, and what we've just drawn for you is HbA1c. So diabetics that go into your physician and they do blood tests, that what they're looking for is HbA1c. That tells them how much extra glucose you've had because they're measuring how much glycated hemoglobin you have. And we'll maybe talk a little bit next time about other health problems that come when you start to do this on your proteins. All right, see you Friday.